Hey everybody, welcome back into another fun and exciting geometry class. Today we are going to be talking about lesson 2.4, Isosceles Triangles. That is on page number 55 in your book if you're following along. Page 55. One thing that we kind of need to just refresh, I'm sure that you remember, but what is an isosceles triangle? Well, an isosceles triangle has two equal sides. It actually could have three equal sides, and we'll talk about that in a little bit. But it has to have two equal sides. It's required. If it doesn't have two equal sides, then it's not an isosceles triangle. So if you look down, I have one drawn here on the screen. And you see that it has two equal sides. All right. So this side, and let me label my triangle. I should have labeled it. So we'll call this A, B, and C. Okay, so A, B, and C. Well, if AC equals, in this case, BC, and I write that down, I mark it, somebody tells me that, it's a given, then I have an isosceles triangle. Theorem number 3 says angles opposite equal sides of the isosceles triangle are equal. Okay, so what does that mean? Well, look, here's a side, and it's an equal side to this side. So the angle opposite, look at that right there. Okay, opposite means on the other side of. So this angle would be equal to this angle. So in other words, A would equal B. How do we know that? Because Theorem 3 tells us that. Why does Theorem 3 tell us that? Because Euclid proved it. I want to show you this proof. I'm not going to show you all the proofs, okay? Trust me, I'm not going to show you all of Euclid's proofs. But this one I think is very interesting, and this one's going to help us to understand some things. So let's take a look at Euclid's proof of this. How did he develop this? How did he figure this out? Okay, there's one thing in particular that I want you to understand about this proof, so that's why I'm showing you this one. And here's what he did. He said, all right, my given, I have an isosceles triangle. AC equals BC. He said, okay, I have this given. I measured this. Somebody told me this is what's given. Okay. Now remember, what are we proving? Well, we're proving Theorem 3. This is what we're working to prove. So we're looking to prove these angles down here are equal. So how did he do it? Well, number 1, he was given, and he wrote given. Number 2, he drew CD to bisect angle C. Wait, what? Where's CD? I don't see CD. It's not there. Let me show you this down here. This is called, and this is in your book on page number 55 at the bottom, an auxiliary line is a line constructed to help establish proofs. So, at any point in time, you can construct anything you want to construct. We've already done, I think, 8 or 9 constructions. So you can use any of those constructions to help you to establish your proof. So if we go back up here to our isosceles triangle, we, using construction, I'm not going to actually do a construction here, okay? I don't have the time. But I'm going to draw a line here, and that's called an auxiliary line. It's not perfect, and it's very hard for me to get it to be perfect. So I'll just leave it right there. Now, typically when you draw an auxiliary line on a proof, you dot it. I'm not going to dot that line, but if you look in your book, the line is dotted. And the reason why they dot the line is because they're showing that that wasn't there when they started. I'll draw it in a different color there. It's blue on my screen. So we drew that line. How did we draw that line? We bisected angle C. That's the line. How did we bisect angle C? By using a construction that we learned. So if we come down here, we say we drew it. How did we draw it? The reason to me is construction number 2. Construction 2. And that is where we learned how to bisect angles. Okay, so we use construction 2 to bisect the angle. And you're like, I don't understand why. You don't have to understand why. Euclid understood why. Okay, so I think you'll follow this once we get to it. What Euclid did was he actually on this one, if you kind of read a little bit and kind of think through what his process would have been, he started from what he wanted to prove. He wanted to prove A equals B. And so he kind of worked his way backwards, and he thought, I need a line right there. If I don't have a line right there, there's no way I can prove that. So he worked backwards, and he said, okay, then I'll just bisect C, and that will give me a line. And now what he did was he actually labeled this point D. So now he has a new point. And look what else he created. He created new triangles. Okay? Now this is why I wanted to show you this. There's 2 reasons right here. First of all, that you can construct anytime you want to construct, you can construct. And so that works out just fine. Now, angle ACD equals angle BCD. ACD, okay, now again, we're kind of lost right here because we're just reading letters. ACD, okay, equals BCD. Okay. So what he's saying is he's saying that this angle right here equals this angle right here, these 2 little angles. How do we know that? Well, we just bisected it. What does bisect mean? It means, put 2 lines on that, it means to cut in half. So if we come down here, the reason for number 3 is, I would call it definition of angle bisector. Definition, I'll write DEF of angle bisector. When we bisect an angle, it cuts the angle in half. It gives you 2 equal angles, and that's in one of our informal statements, I believe. I didn't look that one up, but it's there. When we bisect an angle, we cut it in half. When we have it cut in half, it's equal. So what do we have right now? In fact, I got to get rid of this because we haven't proved that yet. We're working to prove that. So right now, what do we have? Right now, we have an angle and a side. We're trying to prove these congruent so that we can prove that those angles equal each other. That will prove theorem number 3. That's what we're going for. We're trying to prove theorem number 3. Euclid is trying to prove theorem number 3. So the next thing that he did was he came over here and he said, hey, check this out. Side CD equals side CD. You're like, of course. Well, look at this. Side C, what is side CD? Oh, that's the side he drew. That's the new line that he drew. So you're like, so Mr. Steve, you have to say that CD equals CD? Yes, you do. And there's a reason for that. Because CD, check this out, CD is part of ACD, and it is also part of BCD. That line, that's an adjacent line. It's cutting those 2 angles, those 2 triangles in half. Basically, it's bisected that angle, and it's sharing that side. So because of that, we need to write that it is equal. And why is it equal? Well, the reason it's equal is because of what we call identity. Identity. It's the same. It's itself. CD is CD. That's like saying 5 equals 5. Of course it does. Okay? Because of identity. Now, we would come up here to this thing now, and we would I would write 3 marks on it. And you're like, well, it doesn't have 3 marks anywhere else because it's equal to itself. You just put 3 marks on it, and that means it's equal to itself if there's no other ones with 3 marks on it. Okay? So here's what we have. We now have a side, an angle, and a side. So what do we have? We have congruency, side angle side. So if we come down here, the next thing that he proved was congruency. And what would be our reason for the congruency? It would be side angle side. And that's, you could write theorem 1 there if you want. I'd rather you write side angle side. Don't write theorem 1. Forget I said that. Next, number 6. The last thing is that angle A equals angle B. Now, we haven't proved that yet. We proved congruency, but we haven't, and you're like, yes, we proved it because we proved congruency. Not really, okay? And this is where a lot of students run into some problems here, is because they think, oh, I proved that already, because as soon as I say congruent, that means everything is equal. And you're right. But what we have to say is, remember a couple lessons ago when I told you that CP-CTE, congruent parts of congruent triangles, are equal. And we have to say that, because if we don't, then we kind of leave it with no reason. So we have a statement with no reason. We can't have that. So we'd have to say number 6 is corresponding parts of congruent triangles are equal. CP-CTE. That always reminds me of like something from Star Wars or something, you know, CP-30 or R2-D2 or something like that. So CP-CTE. All right, congruent parts of congruent triangles are equal. And when we do that, now we say A equals B, and that's what we were going for in the beginning. We wanted A to equal B, and so we got it. Put 4 of them on there since we have 4 different things. Okay, so there we go, and that was Euclid's proof that is actually true. And it is true, and it's true every time. So now you never have to prove that, because Euclid already proved it. Thank you, Euclid. Now I don't have to keep proving it. So now every time that you need to say something about the opposite angles of an isosceles triangle, now you can say it because Euclid proved it with theorem 3. So you just have to say, oh, theorem 3 says that, and then you're good. Okay? Theorem 3 has a subpoint, or what we call a corollary. Corollary 3.1 says equilateral triangles are also equiangular. And this makes sense, and let me show you why. I thought I had one written down. I guess I didn't. And I'll show you why this makes sense. So if I write an equilateral triangle, let me go this way. We'll call that equilateral. So we'll call this 7, 7, and 7. Those are equal sides. What Euclid said is now, because of the isosceles triangle thing, that must mean that this opposite angle is equal to this opposite angle, right? But now watch. This side is also 7, and this side is 7. So now this opposite angle is also equal. They're all equal. They have to be equal based on theorem 3. So corollary 3.1 would say that if it is equilateral, then it is also equiangular. So any equilateral triangle would also be an equiangular triangle. All right. Lots of fun stuff there. Hope you enjoyed that. We'll see you later. Have a good one. Bye-bye.